of Camels and Committees. Standards should enable innovation, not strangle it. Abstract. When developed and tested widely, standards such as SystemVerilog and UVM can have a profound impact on both users and tool developers. Users benefit from having a common code base that they can use across multiple tools, and the tools developed benefit from them, ideally only having to support one language or a library, freeing them up to the developed tools and technologies to improve the lives of their users. However, keeping in mind the old maxim that a camel is a horse designed by a committee. The downside of a standard of development is that all standards eventually reach a point of diminishing the return, while a standard is able to deliver on the needs of the vast majority of the user community, but development in the community continues to be driven by a few atypical users who continue to try and include more pet features that they believe will make the standard better. Unfortunately, these features often make the standard bloated, more complex, inefficient, and many times incompatible with the previous version of the standard, taking away from the primary goal of providing a stable platform to the user community. This paper takes the position of SystemVerilog and UVM have both reached this stage that rather than continuing to add features driven by the small percentage of the user community, a cooling off period should be adopted to allow tools developers stable platforms on which to innovate. Note, this paper assumes their working knowledge of SystemVerilog and UVM insofar as we will be discussing the specific language, data library features, and their pros and cons, and without providing a tutorial on basic UVM functionality. Keywords SystemVerilog, UVM functional verification and standard. Abstraction, stimulus. Chapter 1 Introduction. The ideal of a standard for EDA was concisely captured by the current president of IEEE Standard Association, Karen Barson, whose first commandment for effective standard is to cooperate with standards and complete the project. The evolution of SystemVerilog and Universal Verification Methodology, UVM, shows the value of this idea. Before these standards came along, users were limited either in having the use of hardware description language, HDR, like Verilog or VHDR, to create their test benches, or to use the appropriately hardware verification language, HVR, which locked them into a particular vendor since the HVRs were tool-specific. The extension of the HVR proved to the HDR by themselves were incapable of effectively modeling the environment to adequately verify the increasing complex design being developed. There were two essential features of HVRs that drove their adoption. The first was the ability to describe objectives that were allocated at runtime, allowing the greater flexibility in describing the test bench. As opposed to the HDR, where all components were instantiated statically at elaboration time. So the second was the ability to specify the constraint to allow the solver to choose randomly from the predefined solution space. Combining these two capabilities meant that verification environment could be created algorithmically that permitted randomization of the environment structure as well as the stimulus data that flowed through it. For example, based on the size and structure of the statistically elaborated design under test, a test bench could be created algorithmically to match the duty layout, as well as the randomly attach additional component to the bus to generate additional traffic. In the development of the SystemVerilog, the decision was made to codify the constraint syntax and semantic, but the committee widely decided not to standardize on the solver algorithm to be deployed to reach a solution. This led to a great deal of competition between tools based on their solvers' ability to achieve maximum coverage of a solution space in the shortest amount of time. Indeed, The authors recall the earlier 2000s when the Einstein puzzle was often used as differentiators in marketing representations, arguing the superiority of the one tool or another. Such competition allowed for innovation in this important area of tool development, which has had a profound impact on user productivity. HVRs were developed in part due to the recognition that as a functional verification is really a software problem, not a hardware problem. Where HDR were adequate to describe the static hardware in the chip, the inclusion of randomization, object, and other HDR features allowed to the language to describe more dynamic behaviors required to describe the high real world in which chips are expected to operate. The users quickly realized that this environment could be quite complicated, and reinventing new environments from scratch for each project was not a viable strategy. Thus was born the concept of verification methodologies to facilitate the reuse of verification IP. The both where is one the where is the elaboration time. The both Verilog and features are supposed to generate a statement, but their ability to specify algorithmically the layout of an environment is limited by a simplistic construction. So the first verification methodology was language specific and were tool specific, and the earlier HVRs were themselves tool specific. Once a user had chosen a language and a corresponding simulator, it was exceedingly difficult to change it to another vendor, since it would have meant having to rewrite the test bench code in another language. Even with the advent of the SystemVerilog, there were still competing methodologies, some of which relies on a proprietary language extension or underlying PLI code and therefore still locked users into particular tools and vendors. Even as multiple vendors claim to support the SystemVerilog standard, even when the users didn't stick to the common subset of SystemVerilog supported by all vendors, their private methodology prevented exchanging the verification IP written by others with an incompatible methodology. These particular problems were solved by the standardization of the UVM, which is implemented in SystemVerilog and is today supported by all major simulator vendors. There are, however, many lessons that the UVM committee and can learn from the SystemVerilog standardization effort. Unfortunately, it is too late to apply some of these lessons to the UVM, even retroactively, but they should give the committee some food for thought in considering future UVM development. Chapter 2. SystemVerilog as a cautionary tale. SystemVerilog has its root, its language called SuperLog, which began developed in 1999 by some of the original creators of the Verilog. It had the lofty goal of being the next generation of HDL and HVR by replacing the Verilog with more modern language features. Replacing Verilog with a more modern language. However, users were unwilling to start from scratch in order to get the language into production. They had large database of Verilog design and test bench code and would only accept a revolutionary approach, not a revolutionary approach. Sorry? Okay. They had large databases of Verilog design and test bench code and would only accept an evolutionary approach, not a revolutionary approach. So, SuperLog was redesigned to be 100% backward compatible with Verilog. Eventually, SuperLog was donated to the Auxilia and became the basis for the first version of SystemVerilog 3.0 in 2002. SystemVerilog started out as a project to consolidate the proliferation of a number of different languages, including Verilog, Spanman, and Vala into a unified design and verification language with the hope that would be reduce the overall knowledge required when developing a complete verification environment. That is, the syntax and the semantic of defining the function is always the same. Over the last decade, SystemVerilog has become a dumping ground for many great features as well as a few not so great. What began as a 140-page set of the enhancement to the Verilog is now a 1400-page tome. Unfortunately, the people picking up that tome, they do not have the historical perspective behind many of these features, nor would you expect them to do. It is extremely difficult to remove any features from the SystemVerilog LLM unless you can prove that no one has implemented it, or if it has been that no one has been able to use it successfully. A few examples: these problems are always comb versus always at star, associative arrays with the wildcard indexes, and a problem of blocks system blocks. System blocks, just over, just a period. Okay, blocks. So the Verilog 1364 2001 added the ASR construct to the automatically generated sensitivity list that enables execution of the block based on when any signal used in an expression inside the block, in the example of the A or B, changes. SystemVerilog, whose development came before the release of the Verilog 2001 standard, created a similar construct to solve the same autosensitivity problem, but went a bit further, solving a few other problems. What if A and B turns out to be a constant? Then there is no change, and the other and out remains uninitialized. That means the SystemVerilog already could solve that by guaranteeing execution at least once at time 0. Now there are two constructions in SystemVerilog that do almost the exact same things. Unless you read it here on in some other guidelines, you would not know to only use always comb. Wildcard index. Vera has a much simpler type system than SystemVerilog's parameterized multi-dimensional aggregate type system. An assistive array in Vera could only be declared with a wildcard index type. A wildcard is simply an unsized integral type, so the SystemVerilog added the ability to declare the array index with almost any user specified type. The SystemVerilog also added a for each looping the statement that can iterate over the element of associative array. However, for each loop will not work if the associative array index was declared as a wildcard type. So there is no longer any reason to use the wildcard type in the first place. So the program block also came from the Vera specification language, which was donated to the SystemVerilog. In Vera, a program was a single procedure that represented the test. Your test was started at time 0, and when the test terminated, the program terminated the simulation. If you needed multiple test threads, you either had to use a fork statement to start it or use multiple programs. When the last program terminated, the simulation terminated. The event method completely replaced the need for any of that test control from a program block. The program blocks also try to mimic the scheduling, the semantic that the PLI application has interacted with the Verilog simulator and tried to eliminate racist conditions between the test bench and DUT. But another SystemVerilog constructor, the clocking block, takes care of races just as well. However, there is nothing in program block semantic to prevent races within your test bench, and prevent races within a designed verification engineers need to be understand the same functionality Verilog schedule semantics that a designer needs to. those semantics would be easier to learn without a complication of program block semantics. Chapter 3, UVM History. The standardization of the UVM, a direct result of users driving the process in the accelerate to reach consensus on a single methodology to support the development of modular, scalable, and reusable generic verification environments. At the time, the two competing SystemVerilog-based methodologies were the open verification methodology (OVM), jointly developed by Mentor Graphics Corporation and Cadence Design System Incorporation, and the verification methodology manual, the VMM, developed by Synopsys Incorporation. After developing an interoperability library to allow the OVM and VMM-based class libraries to be used together, the committee set its sights on developing the UVM. There was no debate about using SystemVerilog as the HVL in which to implement the UVM-based class library. According to the Darfur-Blind study conducted by the Wilson Research Group in 2012, 65% of the respondents were using SystemVerilog for their verification, while other proprietary HVLs were used by only about 15% of the respondents. Also driven by the end users and committee, consensus was quickly reached to use OVM as the basis for the UVM. However, in attempting to incorporate ideas from the several precursor methodologies, the committee unfortunately fell into some of the same problems that plagued the SystemVerilog. The UVM committee was breaking the new ground in actually developing the code as a reference implementation of the standard, which served as a documentation to do the combination of history, accepted practice, and legal constraint. It is documented API to UVM that is officially considered the standard. The reference implementation is technically just a proof of concept, and anyone is allowed to develop their own implementation of an UVM library, as long as it conformed to the documented API. This conformance to the API is what allows users to write their own code that makes the use of the UVM and compile and run it within a UVM implementation, whether it is run with the approved reference implementation from Axera or a vendor-supplied implementation, which might include some non-standard extension. The committee released the early adopter version of the UVM 1.0 EA early adopter in May of 2010 and followed by the UVM 1.0 in February of 2011. Since then, the committee has continued to develop and is at the time of this writing working on UVM 1.2. During this time, the UVM library has continued to grow in size and complexity, as shown in Table 1. Approved 2009. The respondent did not know which company had commissioned this study. The data evaluators did not know the affiliation of individual respondents. For more in-depth analysis of the study, primary C5. So the Table 1 is the size and complexity of the UVM releases. Okay, based on a latest merges of this writing, numbers may change. The primary reason for increase in size between 1.0 P1 and 1.1 was the inclusion of phasing 1 in 1.1. This was an attempt to provide a set of predefined methods to subside it in a long phase, which is only task based on method executed by all components in a UVM test bench. Figure 1, phasing in UVM. The original intention of the runtime phasing mechanism was to allow the users to arrange to set of the tasks would be cancelled automatically in predefined order to the users could group similar functionality across the multiple components into the same phase. However, the devil, as always, was in the details. when the committee attempted to document exactly what operation should be done in each of the phases, it was not always possible to agree, leaving the open the possibility and the component developed by different teams of companies, while each could be in the compliance with the standard, might do specific action in different phases. A further requirement was to allow the user to find their own phases and either create separate schedules of phases to be run in parallel with the original set of phases, or to insert their own phases within the predefined schedule. But the requirement that ultimately doomed the usability of the time phase was the ability to jump backward and forward between phases. As with any complex system, there was a number of moving parts that proved difficult, if not possible, to mesh together. Because of inability to account for the sequences and other possibly spawned behavior in a given phase being adequately controlled when a phase was prematurely terminated via a phase jump. The committee recommended that a runtime phasing method only used from a test to standard to start a sequences and the components such as driver and monitors not implement any of them and just implement the long phase. Jumping, especially backward between the phases, is discouraged. Of course, if these methods are only to use the executed sequences, that then there is really no need to use them instead of virtual sequences, which provide greater control of flexibility in orchestrating the execution of sequences from a test. So, it is interesting to note that the incursion of phasing was considered a top priority, and the UVM from the beginning, although over 4 years later, we still do not have a fully accepted solution for runtime phasing, nor does one appear imminent. However, the lack of these particular features do not appear to affect the usefulness nor adoption of the UVM, as the 2012 study showed the UVM usage has grown 486% since 2010 and is now used by the pluralities 41% of the industry, followed by the UVM, which doesn't include runtime subphrases, either at 34%, followed by the VMM at 20%. Unfortunately, having included runtime phase in the UVM 1.1, there is no portion of the user community who are deploying at least a portion of this functionality, making it extremely difficult to remove it from the standard. Even though the implemented functionality doesn't meet the original requirement, this highlighted the danger in releasing complex functionality in a standard before it has chance to be properly vetted by the user community. The large jump in complexity proposed for the UVM 1.2 is due primarily to the proposed incursion of enhancement to the messaging and transaction recording capabilities of the UVM that, in the author's opinion, are the epitome of the niche features uh, being driven by a vocal minority of the committee that will not have a substantial positive benefit for the majority of the UVM users. As eloquently expressed by a Baroness Bijan Stroopse, the developer of the CETA Plus in October, in an October, in an October, in an October 2013 interview, only by providing something almost universally great to the genuinely useful can we make progress. A standard committee is no place for single issue fanatics. So, oh, fanatics. Okay. In fact, since the proposed enhancement break backward compatibility, they could actually have a negative impact. It's therefore important to standard when a standard may or should be considered done. We will explore the impact of these and other proposed changes in UVM 1.2 later in this paper. But it's our experience with the SystemVerilog standard itself has taught us to be wary of the impact of such late addition to the established standard. Chapter 4 Specific issues with the UVM. A. UVM messaging. Up through UVM 1.1d, UVM messaging has been handled by a set of methods that allow the user to issue a message with an ID associated with it, as well as particular civilities. These messages are delegated to a core component called the UVM_report_handler that can be configured to control whether certain messages are printed to standard out a load file or are suppressed altogether. The report handler also allows users to customize the appearance and the layout of the messages, and the macros themselves allow for the inclusion of the file and the line number where the message is originally created. Command line option, the UVM method allows the setting of the privacy of the per component and per hierarchy basis to separate the reporting of certain messages. In addition, the specific action may be defined for messages based on the message ID and or the severely. This facility has served the UVM users well for years. One of the proposed enhancements to UVM 1.2 is to allow the inclusion of multiple fields in a message, requiring multiple macros to be employed for each message. It also includes the option of a specific context, that is the UVM_report_object in which the message is to be printed. Since the messages can be of type info, warning, error, and failure, this is 16 new macros plus another 4 macros to add a field to the message object. This add macro allow you to add integer strings, string pairs called a tag, and a UVM_object as fields of messaging objects. The proposal adds additional complexity for limited additional functionality. The value of added functionality is questionable as well. In 1.1 section, actions could be assigned to an entire message. By adding the additional field to a message in 1.2, it's now possible to apply different actions to different part of the message. So part of the message might be displayed while another might not be displayed but could raise an error condition. This is another example of complex functionality being raised without field testing it in a substantial group of users or fully understanding the usability aspect of the feature. Our measurement with the proposed codes at the time of the test writing shows a 20% performance penalty when using the proposed extension to print messages as proposed 1.1d. When the message is issued via UVM info macro call. For example, the UVM uses the privacy for info messages only. The ID field of the message checks if the report is enabled for this particular setting. Then it processes any callback associated with the message via the report catcher, and finally it processes and output the message. The 20% of performance penalty occurs without adding the additional text to the messages. It is just the additional overhead based on the additional processing required to handle the case where there might be additional fields associated with the messaging. B. UVM transaction recording. And the UVM transaction recording allows the information about a specific user's object to be recorded into a simulation debug database. Since each simulator has its own format and generic API was chosen for each simulation vendor could provide an implementation to code the appropriate recording to occur. And the reference implementation provided by the Accelerator along with the state standard, this recording takes the form of ASCII format to a file. The proposed change to the transaction recording the API are backward compatible with 1.1D and requires simulation boundaries to provide mechanisms to support transaction recording. Depending on which version the user is deploying. In addition to this, to edit the support burden on vendors, our performance management indicate 65% slowdown relatively to a 1.1D. When the recording transaction is straightforward example discounting the amount of time required for actual file I/O. For the same example in 1.1.1D, the transaction recording overhead was 76%, while for 1.2 it was 126%. So it is our opinion to additional functionality is worth that much over performance degradation. The chapter 5 is a changing verification landscape. It's not the intention of the authors to dissect every proposed change to the UVM between 1.1D and 1.2, 1.1D and 1.2. Rather than we believe the issues raised above indicate that there may be a fundamental issue with the competitive approach and that the more cowbell is probably not the right solution. Rather, it is important to realize that the SoC verification has changed in the year since the UVM standardization began, and certainly it has changed since the precursor languages and methodologies were developed. The Wilson Search Group study shows that data SoC design have become considerably more complex over the years, evidenced by the following data point. The average number of gates of logic and data path excluding the memories has risen from the 400 kilogates in 2004 to 11.1 million gates in 2012. The average number of embedded processors has more than doubled from 1.06 in 2004 to 2.25 in 2012. In 2004, 52% of the design had one or more embedded processors. In 2012, the number is 79%, with 29% having 3 or more. Okay. The increase in the complexity has led to a new requirement for verification that weren't reality counted for when the UVM was initially developed. Clearly, the advent of the embedded processors has led to a realization that the software is now a critical piece of the system, and therefore a large part of the functionality to be verified is specified in the software. If one considers that the ultimate goal of the verification team is to ensure that the chip and system will work when deployed in field, the ultimate goal of functional verification must be accurately model the real world in which the chip will operate, and ensure that both the hardware and software that specify the functionality will react correctly, subject to the full range of the possibility described by verification environment. We used to have a luxury considering hardware and software verification is simply to be making sure that the embedded processor could successfully talk to the hardware blocks to configure them, perhaps to initiate the data transfers. Such behaviors were relatively easy to mimic the UVM by replacing the processor mode with the UVM verification components that could initiate the desired operations as a bus master through the use of UVM sequences. When the blocks were properly configured, the UVM use of the SystemVerilog constrained random data generation compatibility would be deployed on an external stimulus to the design to try and reach certain constant cases of functionality based on the interrelationality of the SoC block connected to those interfaces. So obviously the approach is much more likely to be successful with the design of 400k kilogates, 1000 gates than one with 11 million gates. The problem with constraint random solvers as their semantic are defined in SystemVerilog is that it is possible to often likely you will repeat the random values before they exhaustively cover your desired functionality. Figure 2. Typical functionality coverage curve. When relying on the random interaction of the stimuli across the multiple interactions to the exposed system-level corner cases, such leveling of the coverage is to be expected. When this happens, the only recourse is to modify the test case although the constraint hope for a better result. Of course, in large systems, the overhead associated with solving such a complex constraint equation also negatively impacted verification productivity. In skipping the split of the innovation shown in the SystemVerilog by standardizing the solver algorithm. The UVM expanded the possibility for innovation so that this particular problem may be addressed. So another problem with the UVM sequence-based approach in hardware-software verification is that while it was somewhat useful in ironing out the basic problems on the bus, there was no easy way to replicate the behavior of the UVM sequences learning on the processor standing verification component is software learning on the actual embedded processor model, or even an ISS model of the processor. Therefore, in migrating from block level to system level verification, a discontinuity was invariably introduced the required additional development of resources to ensure that verification areas when learning actual software were still valid. And of course, with the introduction of multiple processors, the problems become more pronounced since there was more software that must be verified, including the interactions between the software thread on multiple processors via shared memory, caches, other complexity. In fact, with complex protocols like the ARM, ACE, AXI coherence extension, the bus fabric itself has become a subsystem that must be verified no longer as the interconnect of simply as a set of individual communication paths between the components on the bus. Instead of interconnection now integrates caches, memory controllers, and other functionality and is in many cases its own network used to connect many components to each other. It is exceedingly difficult, if not impossible, to be able to write constraint random sequences to be run on multiple UVM components connected to such a fabric and rely on the constraint random result to generate all of the scenarios required to verify the cache coherency of the system. Chapter 6. Actual UVM requirement. In just this brief exploration of my multiprocessor SoC verification requirement, we can see that the constrained random capability of a SystemVerilog, on which much of the UVM is based, are no longer sufficient to meet the productivity requirement of today's SoC designs. Rather, what is needed is a new way of building on top of the UVM test environment, the ability to specify the stimulus and encourage at a higher level of abstraction that can be used as both UVM sequences and as software, and better cover the desired state space with repetition. A large composition of multiple state spaces into a system level space with no loss of effectiveness. When one looks at these requirements, it is reasonable to make the argument that UVM, as currently constituted, provides an ideal platform for user-specific verification infrastructure while allowing to developers the freedom to innovate to attempt to solve these problems through the further abstraction and automation. If one were to propose a solution to these problems, it is easy to see that obstacles that proposed extension in the UVM 1.2 are intended to address the no longer need to be solved in the UVM itself. Rather, the UVM ability to specify a set of verification components can be arranged and configured algorithmically and randomly if desired, paired with the ability to use the UVM sequences that could provide an API for higher level stimulus specification to drive UVM components, means that it is not necessarily continue to expand the core functionality of the UVM. Features. like transaction recording can now be done as part of the higher level tools on top of UVM, so things like transaction linking and advanced debug are taken out of the realm of the UVM. So consider a system in which a bus master must be able to drive the bus in all possible modes. In a UVM environment, the master would be represented as an agent in which the driver would get a transaction from a sequence and use model information embedded in the transaction object and the control interface in signal to execute the transaction in the bus. Consider the hypothetical bus protocol. Assuming 4 possible values for SIG, 2 possible values for RW, 16 possible values for weights, and 10 possible values for X-mid delays, this protocol would involve the 4 by 2 by 16 by 100 equals 12,800 possible variation of the transaction types. Typical coverage models also require that each of these transaction types are performed to different areas of memory, which increases the number of unique bus transactions required considerably. To expect to be able to reach all of these coverage points via constraint random generation is simply unrealistic. That the problem becomes exponential work and multiple master are included. After sequential behaviors require the best write followed by a zero with a single byte write, for example, it becomes extremely difficult to even write the constraint expression to make it happen. So the engineer is reduce the writing coverage point, which is no simple task, and hoping that the random transitions naming eventually hit their desired combination. So instead of separately specifying the constraint and the coverage goals, which in SystemVerilog use very different syntax, it would be beneficial to raise the level of abstraction to a single specification that could guarantee that a set of the transactions generated would cover the desired status case without repeating any scenarios. This abstraction plan specification could thus be used to both generate and transaction, and tools of automation could record interesting information about them that assist in coverage analysis and debug. So in starting with the unabstraction specification, the verification team is represented with the options how actually to map the specification into the verification environment. In a UVM environment, the stimuli are modeled as via sequences, so either sequence code could be generated from specification, or a UVM sequence could be built-in automation hooks into the links to another generation engine would tell the sequence what transaction to generate next. In either case, the user would simply specify via the UVM test to run an automated sequence. The modularity of the UVM allows the rest of the UVM environment, including the agent, scoreboard, and other components, including the other constraint random sequences, if desired to continue to reuse without modification. The UVM is an ideal platform to allow such automation, which is quickly becoming a requirement to be included in the verification process. Another advantage of abstraction specification is that it allows for other options besides just interacting with the UVM sequence. As mentioned, the ultimate goal is to ensure that the software running on the processor successfully interacts with the environment. The abstraction specification would allow the transaction stream generation to accomplish as software running on the processor model as well. Other than replacing the bus master UVM agent in the processor model, the rest of the verification environment wouldn't need to change, demonstrating against the value of reuse in the UVM. However, if you could link the abstraction specification for the software on an abstraction specification for the external, that is the real-world stimuli, the automation would then be able to generate scenarios where the software would react to the specific behavior the final design is required to handle. Using the same analysis, optimization, and generation capabilities previously discussed, all of these scenarios could be achieved automatically, guaranteeing that we reach our coverage goal. Chapter 7 is conclusion. The standardization of the SystemVerilog and the UVM has been a substantial benefit to our industry by having a single language that combines hardware description, verification assertions, and the DPI. SystemVerilog provides based on assertion, which additional functionality can be layered. The growth and success of the SystemVerilog assertion SVA library is one such result. Nevertheless, one must admit that SystemVerilog, while incredibly useful and successful, is not really the ideal language. If a small group of unbiased, dedicated language designers had set out from the beginning to create a single language that addressed the content of the original SRE committee, there is no doubt that while much of the language might look the same, there are parts of the current standard that would not be there, having been adopted in the committee through the political, historical, or other reasons. Similarly, the UVM has undoubtedly been a success, but because of the nature of standard committees, particularly the case of the UVM committee attempting to develop software along with the standard, the library includes many overlapping, redundant, unnecessary, and in some cases, contradictory features. Over the course of each development, the requirement for SoC verification has changed, introducing the need for high level of abstraction and offering the opportunity to innovative tools to take advantage of the UVM ability to build a modular verification environment to provide additional capabilities that are not available in the SystemVerilog. So since their successful SoC verification will require the use of such innovation tools above and beyond what the UVM offers or what is proposed in UVM 1.2, and makes little sense to continue building an additional functionality that slows down the core of UVM, thus making it less useful as a platform for innovation. The purpose of standards is to enable innovation, and standards must be bounded to provide efficient, stable platforms so this new generation of tools can focus on providing values, not being compatible with multiple versions of underlying standard. Unfortunately, continue to tinkering with the UVM and SystemVerilog threaten to make each standard less effective rather than more. Okay. Today, I read this paper of Camels and Committees from DVCON 2014. Okay, thank you for your time. See you next time.